Right, so I am discussing about the SM subject. The topic is my on simply supported beam with shear force and simply supported beam. Cantilever beam with point load. How can solve the problems and given more example in this topic. So there is that some more example problems. So cantilever beam with point load and uniform distributed load. Discussion about that and create that. That is the problems. First problem we can discussion about that. So draw the shear force bending moment diagram for cantilever beam and shown in the figure. So directly in the example problems given that some problems. So somebody said given in theory there is that one is a cantilever. This is the cantilever beam and a total cantilever beam one side the fixed and one side and other one is the free end. Free end means there is no there is and here total length of the beam is 1 meter, 2 meter and 1 meter. So that is the problems and load is applied here. Point load is 30 kilonewton and EDL load is 25 kilonewton per meter. There is no appearing m. That is how can give the solution here. And first of all we can calculate the shear force. So shear force at the point of B. So there is the no given the point. So point of the B 30 kilonewton and from the distance is there is load not considering here and shear force at the D point and here point also be known as specification specified that her A and B C and A B C D there is no problem base we having from the D distance 1 meter and 2 C is having 2 meter from the D and A is having from C to 1 meter. So we can calculate that shear force at the point of 30 kilonewton as given here problem. So 30 kilonewton and shear force at the point of D and having the same force is also be here given. So there is inside the here the point there is no load the 30 kilo also be B point and however working at and somewhere so that is that reason of working so just and 30 kilonewton from here so there is that one videos and at the point of C so we can calculate here so 30 into 50 why did you give 50. So here problem is wrong. Somebody's at the C point there is applied two loads only. Here also be one load 50 kilonewton and at the point of A 50 and 50 into sorry 20 into 2 sorry right and 20 into 2 there is a calculating here directly here also be right now 25 um, into 2 so that is the equal answer right. However in this topic we can discussion about that at the C point we know that so 25 into 2 at the C point 25 into load into length we can discussion here already formula we have that and at the point of when here 30 plus and into 25 into 2 plus 25 into 2 there is no distance calculating the front of distance is distance not considering here 2 only considering 2 for 25 into 2 same at the C point what is the load having there is the same as well as A point is also the same 30 80 kilonewton 30 plus 50 is equal 80 kilonewton there is the answer and however so bending moment we also be calculation of the bending moment how can we can know that so bending moment bending moment at the point of B is equal to 0. Why did here 0? The front in front of the B there is no length. So length L is equal to 0. That is W into L is also be calculating that L is equal to 0. Total will be 0. And so bending moment at the D and bending moment at the D will also be known. So 30 into 1 there is a calculating here 30 and force is applying upward direction. The bending in the bending moment we know that when it giving the upward direction, that is the negative. So there is a formula. So we know that minus 30 into 1 is equal to 30 kilonewton meter. And however at the point of D also we calculated the at the point of C. So 30 into 2 plus 1, we know that 30 into 2 plus 3 3 2 plus 1 3 minus and 50 also we know that 25 into 2 plus 1 by 2, we know that 25 by 2, we know that 1 by 2. So we can calculate that there is that 50 into 1 and at the point of C 50 into 1 and 50 into there is a 1 50 into 1, so 50 into 50 into 2 30 into 3 and 50 into 1 and then calculate with that that is that 90 and plus 50 is equal to minus 140 kilonewton. And however at the point of 30 here 30 into 1 plus 2 plus 1 4 and there is considering the length is also be 30 into 4, so you can write now here 30 into 4 and 50 into 2 2 into 2 50 into that is calculating 50 into 2 2 and we can calculate that 30 into 4 is equal to 120 and 50 into 2 is equal to 100 is equal to 220 kilonewton meter. That is the answer of at the point of A. So 220 is the correct answer. And here there is a in the graphs we also we draw that shear force diagram. This is the shear force diagram and this is the positively totally positive xy above the axis, we can draw that above the axis. And however we can know that uh, here shear force diagram, so positively totally, so place 30 kilonewton here from point B to here, so upward direction we can draw that and then horizontally up to D point, so there is the equal of 30 kilonewton at the beam. And however D from D to C and there is a EDL load, we can draw the inclined line. So there is that here to here. So what is the increasing of 30 kilonewton meter? So here 30 kilonewton. So we can write now at the point up to 70 80. There is that changes. And however at the C to A point, C to A point we can calculate same direction from C to A. At the point of C is the 80 and at the point of A is 80. C is equal to A. There is no load changes, equal to load equal. So there is a straight line, we can draw that and however you can change the coincide the horizontal line. There is the vertical and horizontal, we can draw that. This is the diagram of shear force diagram. However we can draw the bending moment diagram. So the bending moment diagram, we know that at the point of 0, at the point of B 0, there is no force, no length, so 0. And however at the point of from B to D we can calculate that from D also be minus 30 inside the outside, not upper, below the xy plane. We know that the minus 30 kilonewton, we can draw that up to D point, we can incline line. This is the inclined line in the bending moment diagram. And however at the point of D 30 and at the point of C 80 minus, sorry, at the point of is also be 140 kilonewton meter, 140 kilonewton curvatures. So ideal load having here, so curvature we can find out the minus 140 kilonewton meter, right? That is the right answer. We can draw the ideal load when it is appearing ideal load. If there is a draw the some curves of line, and however and C to A from the equal division not equal. So there is a 140. This is at the point of C is a 140 minus, and at the point of A is a 122 20 kilonewton, 120 kilonewton. So there is a straight line, we can draw that and draw the upward direction. So minus 220 is the right answer, and we can join the two lines vertical and horizontal. This is the diagram of bending moment equation. However, and we can calculate somebody. So some problems will be same. Some problems as given in the same subject. How can calculate? How can draw that problems? And in that problems, we can know that next one problems we can discussion about that in this topic. The cantilever beam 40-meter long has point load and 40 kilonewton and 50 kilonewton and 10 kilonewton at a distance of 0.5. Here is here is now 0.5 meter and 3 meter and 4 meter respectively from fixed end, and however it also be having UDL load of 60 from 60 kilonewton meter for a distance of 2, and starting from the 1 meter from the fixed end. And it also be draw the shear force and bending moment diagram. So this is the problem. In the beam is also be known that the we can find out our first of all we can what is the which type of given the beam is. Here type of is cantilever beam given. So cantilever beam means one side is a fixed beam and other one is the free end. That is that calculating is the free end of fixed beam. So this is the diagram of given here. First of all cantilever beam, one is the fixed beam and the other one is the fixed free end. And here point is also the specification. First of all A point, and here B point and E point, D point, C point, A B C, A B C D E. And at the point of B we know that in the problem 100 kilonewton, and E at the point of E 50 kilometer, and we can start our E to D here UDL load, we can draw that in the curvatures. And however at the point of D, and there is no UDL load, and until UDL load, but left side is no, there is no load. And see at the C the point as having 40 kilonewton, and distance also be from given in the example from A is the from fixed point 0.5, and from C, and from fixed point to D 0.5 plus 0.5 1 meter, and from the E point is fixed point 2 meter, from the E free end B point is 1 meter from E. So there is the total distance 1 meter, 2 meter and 5.5. There is a one total having 4 meters. So that is the calculating and different load applying here. So 100 kilonewton, 50 kilonewton. There is a 40 kilometer is the UDL load. Sorry, point load, and UDL load is the 60 kilonewton meter. We know that. And however in this topic we can calculate the shear force. We can find out calculate it. First of all we can calculate that the shear force. So and shear force at the point of B, we know that point of B, what is the distance here? So point of here there is that 100 kilonewton, and however at the point of we know that just one time, and here at the point of 100 kilonewton we can place up any point load in the shear force rules. And at the point of E, at the point of E, at the point of E, we can find out here. So there is no calculate considering of length. So 100 plus 50. Then the force is having upward direction. So upward direction there is the right side, and downward direction up to down is the right side, left side. So there is a positive. There is a plus 50 plus 50 is equal 150. And a shear force at the D point we can calculate here. First we can calculate 100 place point load, and calculating 50 place the force is having upward direction. So top to bottom, and left side is going to bottom to top. And there is the positively 50 plus 50 and 60 into 2, 60 into 2. So there is a 50 plus 50 plus 60 into 2. We know that in the UDL load it is a 60. Also we know that UDL load also we, when it occurs the UDL load into length, we have to formula. So 60 into 2. So there is the correct answer. And then calculating the total negative, so positive, so plus 270, 100 plus 50 plus 120. There is the 270 kilonewton is the right answer at the point of D. So there is the application of total load 270. And at the C point we can know that. So C point, at the C point it also be considering 100 plus 50 plus 40. The force is having upward up to down in the left right side. And here we can calculate that. So 100 plus 50 plus and 40 and 60 into 2. When did the application is having from D to E point, D2 point having UDL load, there is only considering load into length. We can W into L. Formula is having, so 60 into 2. So then substituting here, so 50 plus 50 calculate all the load, 60 120 plus now that 180, and to total having answer is 310 kilonewton is the right answer at the point of C. So having it the same point, when did the given the at the point of C, we can calculate here. 50, 100 place, 10 place and 40. There is no changes, and 60 into 2. And whatever here the C point and also be same, the A point is also be answer same. So A is the correct answer. You can calculate to 310 and 310 kilonewton at the same point of load. There is a total calculation, and we can here also be all positive, negative, and upward direction. Force is having a continually upward direction, up to down. That is our left side. There is a plus positively we can calculate. So plus is the point of is plus, E is the plus, D is the plus, and C is the plus, A is also the plus. That is the cantilever in the cantilever. And bending moment we also we calculate same bending moment at the point of B. We know that at the point of B we can find out there is the in front of B there is no length, that is the length L is equal to 0, then at the point of also be 0. Okay. And however at the point of E we can calculate that at the point of E, and at the point of E in front of calculator, but the left side is not considering here. So 100 into length, W into L, we know that. So W into L, we know that 100 into 1, 100 into 1, 100 into 1. And also we know that okay. And at the point of we can calculate here, at the point of D we also we calculate here. There is that 100 into 3, that is the 100 into 2 plus 1, 100 into 3. The force is having upward direction. So the in the bending moment left side, right side, we can calculate considering negative. So 100 into minus 100 into 3. And also we calculate here 50 into 2, 50 into 2, force is applied upward direction up to down, that in the bending moment is negative 50 into 2. And also here also we can calculate in front of the length at the CD point, and 60 into 2 into 2 by 2, 60 into 2, 60 into 2, 2 by 2 is the one answer, there is no changes. Length having with a 1.60 into 2, 1.5, 1 by 2, there is no changes, 2 by 2. That is the wrong answer. 210, and total we can calculate that 1655 kilonewton meter. And also at the point of A, 100 into, we can calculate total length. What is the total length? 4 meter, minus 100 into 4, and 50 into 3, and 4 into 40 into 0.5. So, and 60 into 2 plus 60 into 2, and 2 by 2, 2 by 2 means 1, and plus 1, that is the calculation is the right answer. So here, 100 into 4 minus 100 into 4 minus 50 into 3, and 60 into 2, 2 by 2, now that calculated, and 40 into 0.5, that is the total answer is minus 810 kilonewton meter. That is that answer is the right answer. So then we can draw the specification how here, calculating the, considering the diagram. In the diagram we can calculate at the point of B plus 100, plus 100 we can draw the upward direction vertically, and with the same load having at the E point, same having 100, and at the point of 50, at the point of E we can raise the plus 50, then upward direction up to 50, and E to D is having a 6 UDL load. UDL load we can draw the inclined line. So from E to D, and there is a at the D point 270 increases. So incline 270 kilonewton increases, right? And positively, it will also be positively, and at the D to C we can considering here points. So D to C we angle 56, 100 plus 50 plus 60 plus into 2 plus also be 40, we can calculate 310 kilonewton, we know that. So that is the problems in that, and also at the point of D to C at the same level equal load, and then rising at the C, and C is rising 310, and C to A we can calculate here, C to A 310, and A is the also be now that 100 we can decrease same. What is the C point load, and same as well as calculating 310 load, there is a no changes, 310 load. So from A to, and you can draw the, can join the horizontal line, vertical line, and it is a fixed of 310 is the final kilonewton, at the total load is the 310 kilonewton, and however we can draw the vertical line, vertical line, hollow in that vertical line, at the draw the bending moment diagram. So at the point of 0 there is no changes, so up to 0, and then start the point E load, 100 load also be applying up to 0. So 100 plus 50 and is equal to 150. We know that in the bend, sorry, 100 minus 100, there is no, in, if not considering in front of considering of length. So the point is 100, B to E is minus 100 kilonewton, and then in E to D is the UDL load. We can draw the curvature, some curvature occurs here, 60, we know that some there is a E to D answer kilonewton, 1 minus 520 kilonewton is below, draw the XY line below the diagram, and here and D to C minus 655. 655 is the right answer at the C point, and there is a draw the inclined line. There is a no curvature curved line, inclined line only, and from C to A and minus 810 kilonewton. So we can draw the again inclined ladder, and we can join the inclined line and vertical line and horizontal line. That is the diagram of bending moment. So 100 minus 100 kilonewton minus 520 kilonewton minus 655 kilonewton meter, and minus finally total bending moment in the curvature minus 810 kilonewton. There is the correct answer minus 10 kilo. This is the diagram of in this problem. So this is the problem. We can solution how can we whichever point of given load or different load, and then increasing bending moment and increasing of equations. So this is the diagram. And also with some more example in the topic. So some okay. In this topic, cues a cantilever beam having point loads and UDL load, the maximum bending moment will be at fixed point in point. So some problems having there is the point the cantilever. Answer is the A is the correct answer. A cantilever beam having point loads and UDL load, the maximum bending moment will be fixed end. The A is the right answer. And frequently asked question, we can discussion about that. A cantilever beam 5 meter long is carries point loads of 30 kilonewton and 30 kilonewton and 30 kilonewton at the distance from 1.5 meter and 3 meter and 4.5 meter from the fixed end. In addition to this, the beam carries uniform distributed load of 10 km. There is a distance of 10 kilonewton meter over the entire length of the beam, and over the length of the beam, and draw the shear force and bending moment diagram. That is calculation. So continue equation we can know that this is the 1 minute, and draw the shear force diagram for the cantilever beam shown in the figure. This is the diagram. uh, Points are not given. A, this is the B, C, D, and there is a point is the from distance fixed beam fixed to C 3 meter, and here also be A, B, C, D. D also be from fixed beam 5 meter, and free end is the total length. We know that total length 3 plus 2 plus 3. There is the 8 meters total length. And UDL load also be known that this is the point of load. And UDL load also be 1 Newton per meter square. That is the given. Not in the topic is 10 kilonewton. There is a not correct answer is this. Uh, this is the 10 kilonewton. 10 kilonewton meter, and point load is 6 kilonewton. Then this is the example problem. We can discussion about that, and also we and some example problems as summary in this topic. Summary we also be discussion about that. In this period, we have discussion that how to draw the shear force and bending moment diagrams of cantilever having point loads and UDL load, and shear force will be maximum at the fixed end of the from calculated beam in this topic. And also we are discussion about that bending moment will be maximum at the fixed end from the cantilever beam. We also did discussion about that, and this is the 4 periods of 4 points having that how to calculate and how to inserting, how can draw the topics. And this is the topic of discussion about that how to draw pen. Somewhere in the topic discussion about some example problems, and that is the this is the subject of civil engineering C18. C18 is the calculating how to can draw the some topic there so be given is okay. Right now that is my topic is over. Right, thank you.
Hello friends, hope you guys having a great day. I'm back with a new tutorial on cantilever beam problem in ANSYS Workbench. Hope you guys like my previous videos on ANSYS basics and how to create a material in ANSYS Workbench. So let's get started. Now today we are solving a square cross section cantilever beam problem whose dimensions are as follows. The length of the beam is given as 4 meter, width of the beam is 0.35 meter and height is 0.35, making the cross section a square. The Young's modulus for this beam problem is 2.7 e raised to power 10 pascals. Now by using ANSYS Workbench, we need to calculate three things. Number one, we need to calculate the total deformation of the beam. Number two, we need to calculate the maximum bending stress generated along the beam. Number three, we need to calculate the bending moment along the beam. Now by the definition of the cantilever beam, a cantilever beam is a beam which is fixed at one end and there is a point load on the another end. In our case, we have a point load of 6 kN at the right hand side. So let's get into the ANSYS Workbench. Now go to static structural module and double click on it to drag and drop into the project schematic window. Now double click on the static structural and rename it as cantilever beam problem. Now the step one is to give the engineering data to the ANSYS Workbench. So double click on engineering data and create a new material and give this material the name steel. Now in order to create the properties of this steel, double click on the isotropic elasticity and these properties will come down here. Now give the Young's modulus value 2.7 e to the power 10 pascals. You can give the Poisson's ratio 0.3, but I'm giving this value 0 here. It will not affect your model or results. Make sure your units is in metric. My units is in meter or metric, so keep that in mind. Now since I have given the engineering data to my problem, now close this engineering data window and now our engineering data section is over. Now to provide the geometry to ANSYS Workbench, double click on it to start the design modeler. Now this will take some time to pop up the ANSYS design modeler. So this is the ANSYS design modeler in which we have to create our cantilever beam. Now select XY plane and make sure to perpendicular it to the screen, and now go to sketching, select a line and create a line of 4 meter. In order to dimension the line, go to dimension and click on the line and give this value 4 meter. I'm creating the midline of the beam, and after that we need to convert it to sketch. Now go to concept, select lines from sketches and click on this line and apply and click on generate. Now since we have created one part, or we can say one body, now we have to provide the cross section to this one part. So go to concept and go to cross section and select rectangular. So this will create a rectangular cross section, but in our problem it is specified that the cross section is square. So give this value 0.35 and 0.35 as the height of the beam. Now click generate. Now go to one part, one body and select line body in order to create the cross section attached to this body. Now click generate and go to File and close Design Modeler. Now since our engineering data and geometry portion is over, we need to enter into the model. So double click it and it will open the ANSYS Mechanical. Now this will take some time to attach our beam geometry to ANSYS Mechanical. So this will create the center line of the beam. Now in order to show the beam, go to View and select Cross Section Solid. So this is our square cross section of the beam. Now before getting along, since our material is steel, by default the material in ANSYS Workbench is structural steel. So go to Geometry and select Line Body to change the material assignment and select steel. Now go to Mesh and click Update to get the default mesh. Now if you drop down this menu and click on the statics window, you see there are 43 nodes and 21 elements in this beam. Now the next step is to apply the supports. Now select Static Structural, go to Supports, select Fixed Support and make sure to highlight this vertex filter and select the left side vertex to apply the fixed support to it. Again select Static Structural to apply load, that is the point load on the right hand side vertex. Select Force, make sure to highlight the selection filter, that is vertex, and select vertex and apply. Now this vector can be changed to components, and in the Y component give value minus 6000 Newton and hit OK. Now go to Solution and select Deformation Total. Again select Solution, go to Tools and select Beam Tool. We need to evaluate this total deformation first and solve. Now this will take some time to create the mathematical model, provide the boundary condition to it, and then solve completely. So you see our model is solved. Now you can see that the total deformation here is 3.8 millimeter. Now if we go to our problem and see our analytical results, that is the deflection for the point load, see that the deflection is 3.79 millimeter. So our ANSYS result is pretty close to it. And one thing here is to notice that our finite element method does not provide us the accurate results. It basically gives us the approximate results of the problem. Now open this beam tool and select the beam tool again and go to Stress and select Maximum Bending Stress. Right click on Maximum Bending Stress and evaluate results. So you see our maximum bending stress is 3.35 megapascals. Now if we see our analytical results of the bending stress along beam, so it comes out to be 3.36 megapascals, which is very close to our ANSYS results. Now we need to have bending moment along the beam. For that, select Model, go to Construction Geometry, select Path. In path type, instead of having 2 points, select Edge, go to Edge Selection Filter and select the center line of the beam. Go to Geometry and apply. Now go to Solution, go to Beam Results, select Bending Moment. Now in scoping method, instead of using geometry selection, select Path. In Path, select your chosen path and in the definition, choose Directional Bending Moment. In the orientation, select Z-axis and now right click on Directional Bending Moment and evaluate results. Now since my units is in millimeter, go to units and select metric. So you see the bending moment is minus 24,000. Since the bending moment is force multiplied by the perpendicular distance, our force is 6 kilonewton and the length of the beam is 4 meters, so that gives us the bending moment of 24,000 in z direction. So this is the cantilever beam problem solved in ANSYS Workbench. Hope you guys like this video. Give this video a big thumbs up and I'll see you guys next time with a new tutorial. Till then, peace out.